Okay, let's start. Thanks everybody for coming. I'm Ed Felton. I'm the co-founder and chief scientist at Offchain Labs. And I'm going to talk about Arbitrum, which is our product now in its second spin of alpha that overcomes a bunch of the limitations of state channels. Basically, I'm going to talk about state channels, just sort of a review of what they are and what the limitations of state channels are. And then I'll talk about sort of how we overcome those and some about the design of our product. And at the end, I'll just give a few pointers on what to do if you're interested in using it. All right, so start with smart contracts. Smart contracts are awesome. They have their disadvantages. Every miner emulates every execution step. So the contract complexity is limited by the global gas limit. On Ethereum, that gas limit is uncomfortably low. It's something like 1/10 of a laptop of total computation capacity that has to be shared by everyone across the world. And this gas mechanism is basically necessary because it's expensive to run contracts. And also, all of the contract and code and data is public. So the total throughput is really limited by what a single miner can do. Right? So there are a bunch of responses to this to try to get scalability. One of them is state channels. And just a overview of what state channels are for those who need the review. You have a fixed set of end participants in a state channel who are defined at the beginning. When the state channel is operating as a state channel, they unanimously agree off-chain about updates in the state of the channel. And as long as they unanimously agree on a sequence of updates, you can stay off-chain and everything is good. And you only need to go on-chain if there's not agreement among the participants. So the optimistic case is great. Everything happens off-chain, and you only need to sort of cash out the state channel at the very end on-chain. Okay, so if you want to write this as a smart contract in Ethereum, you write it sort of like this. You write it as a smart contract that operated in two modes, state channel mode and on-chain mode. So the contract starts out in the state channel mode, and the participants then sign state updates locally. And when you're in this initial state channel mode and everything is going along off-chain, then all of the functions of your contract are locked except for closed channel. Closed channel is basically which is what someone's going to do if you are no longer reaching unanimous agreement off-chain, then you're going to need to move on-chain. So you initially start here, everything happens off-chain except for this one opportunity to close the channel. Now, if you don't get agreement among all of the parties, and that could happen either because somebody becomes unavailable or because somebody is just uncooperative or malicious. If that happens, then some participant can decide to close the channel. Actually, any participant can decide to close the channel just because they feel like it. But in any case, once you close the channel, the contract now enters the on-chain mode. The contract is initialized with the most recent signed state. Whatever is the most recent version that all of those parties agreed to off-chain, that's going to be the initial state of the now on-chain execution of the contract. All the functions are now unlocked, and the contract proceeds on-chain until completion. Right, so you ride the optimistic horse as long as you can, and when the optimistic mode fails, then you switch to on-chain execution. That's the standard state channel model. So why use them? Well, they're fast, they're scalable, fast and scalable because they have very little on-chain footprint in the optimistic case. And they're also private when you're operating in the off-chain mode. That is, you don't need the stuff that's happening in your contract, that can just be agreed upon mutually by the participants, and as long as they all sign updates, you don't have to post those updates to chain. And you can have a long interaction between the parties, and at the end you just have a simple cash out transaction that they both agree to. So that's great when you're operating off-chain, but there's a set of disadvantages that state channels have, a set of limitations. So one limitation is that they're sort of fragile. If one party not only fails, but even just goes offline for a while, one participant, then your fast progress halts. You switch into the slow on-chain mode, and you stay there. State channels don't distinguish generally between unavailability and malice. So it doesn't require that somebody be wrong or malicious, just if they have a hiccup in the availability of their computation or their network, the result will be the whole thing will go on-chain and stay on-chain. So that's the fragility. The second limitation is that they're computationally limited. Although you can do huge amounts of stuff, lots of computation, have lots of storage when you're operating off-chain, you need to be prepared at any time to move on-chain. And that means whatever it is you're doing, it has to be doable on-chain. And so even if you're in the optimistic case, you have to be able to get pessimistic. And so that means you can't do more than on-chain resource limits would allow. So state channels improve the transactions per second, but you still face the same limitations on computation and storage as you would if you were on-chain. The third limitation is you don't get guaranteed privacy. You have privacy of what's happening if you're operating off-chain, but as soon as you go on-chain, everything is visible again. And then finally, generally, state channel models require specialized development. That is, you don't write your contract in the standard programming model or paradigm. You have to write your contract specially for a state transition paradigm in which the contract goes through sequences of states, and what gets agreed upon is the state in between. And that's a different programming model than the one that you have if you're writing a normal contract in, let's say, Solidity. So the fact that you have to write in a different model, and a model that some people at least consider to be less friendly, is a drawback. So those are the 4 limitations. Arbitrum, our solution from Offchain Labs, solves all of these issues. We're able to make, and I'll explain how and why this happens in a minute, but we can make non-unanimous fast progress, meaning that if somebody becomes unavailable, we can still make progress fairly quickly, not quite as quickly as if everyone's available. Even if somebody gets malicious or in error and there's a dispute, we can still make progress relatively quickly. We can resolve disputes between parties without having to run the full code on-chain. We have a very efficient on-chain dispute resolution protocol, which operates without taking more than a tiny bit of the state and putting it on-chain. And that means that because we never have to move your whole contract on-chain, that we're not limited by the computation and storage that we could do on-chain. We can do more than can be done on-chain and sustain that. And privacy is guaranteed even when there's a dispute. Because you don't have to move the state of your contract onto the chain in case of dispute, if you want to keep the code of your contract secret, or you want to keep the state of your contract secret to only the participants, you can do that. And there's no need to explicitly reprogram in the state transition model. You can compile existing Solidity contracts without modification using a compiler that we supply. So if you have, and my colleague Harry Claudner did a API workshop this morning where he did a sort of live porting of a simple DApp from Ethereum into Arbitrum in a few minutes. It requires changing only a few lines of code sort of in the initialization. Okay, so now there are a couple of different use cases or styles of using Arbitrum, which I sort of summarized here in this table. And I'm not going to go through all of this, but I just want to note that what I'm going to talk about here is what we call Arbitrum channels, and that is a state channel-like mode of operation, where there's a fixed set of participants, the system runs trustlessly for the participants, and computation, storage, and messages all happen off-chain. We give instant finality for, in the common case, and privacy is such that only the participants need to know what's going on. We also have an Arbitrum chain mode, where the participants are dynamic, participation is dynamic and open to everybody. It has slightly different performance characteristics because messages to the call data of your transactions has to be on-chain, but computation and storage still off. So I'm going to talk here in this session about Arbitrum channels. Okay, so basically, the Arbitrum design involves, at a very high level, a combination of 3 things. It involves some protocol design, that is, how is it that the participants interact with each other. It involves some incentives. We give parties incentives to come to agreement off-chain, and we produce strong disincentives to ever getting into a dispute. And then we have, there's some things we do in the virtual machine architecture that allow us to make dispute resolution very cheap. And I'll go through this in a little bit more detail. So let me sort of build out how this Arbitrum channels mode works. One of the first concepts here is a validator. And that's a term we use for a participant in an Arbitrum channel. when you make a VM, a virtual machine, this is our term for a contract or group of contracts that are running, sort of for a running dApp on the chain. You give a list of validators for it. Those can be any parties you want. And those validators are responsible for keeping track of the VM's computation and its data. So think of them like the participants in a state channel. And we provide what we call the any trust guarantee. And that guarantee is that as long as at least one of your validators is honest, then we guarantee that your contract will execute correctly according to its code. That means in particular, if you're a validator, then you can force correct execution all by yourself, so it's trustless with respect to you. And that's why we say that Arbitrum channels are trustless, because every participant is a validator, and any one validator can force honest progress. Validators advance the state of the running VM in a couple ways. They have incentives to agree unanimously about what a contract will do. And when they unanimously reach agreement, they can repeatedly update the state without going on-chain. This is very much like the optimistic mode of a state channel. You can have a whole series of executions, and if everyone is well-behaved and follows their incentives, then there's basically one on-chain transaction to start your contract and another one at the end to cash it out. If they all agree, the system accepts what they agree on as correct, and that's consistent with that any trust requirement. So the method that we use is something we call unanimous assertion, and it looks logically like this. The validators all agree that if the virtual machine starts in a state that has a certain hash, and with its inbox of incoming messages having a certain hash, then it can execute n steps of computation. The result will be that the machine state will have this hash, the inbox will have that hash, and along the way it will make some payments and send some outgoing messages. So if all of the validators agree on this, then they can sign a series of these things, and if they chain together with this resulting state matching the precondition of the next one, then they can just chain them together off-chain. Okay. So as long as it's signed jointly by all of the validators, you're good to go. And that's all off-chain. Okay. And once it is confirmed and fully signed by everybody, there's some technical details here, but except in rare cases, it's immediately final. Meaning that we guarantee that it will eventually reach the main chain and achieve finality there. So that applications, clients can trust that they already have finality. All right, so far this looks like just regular state channels. I want to talk now about the more interesting case, which is how to make progress non-unanimously. One of the first pieces of this is what we call a disputable assertion. So any manager, any validator can make an assertion. That is a claim that looks just like one of those unanimous assertions, but it's made by just one party. And when they make this claim, they put down a deposit, which they might lose if they're lying. That assertion is subject to challenge, and if somebody challenges it, claims it's wrong, then they deposit funds. And if there is a challenge, then there's a dispute, and the party that's wrong is going to lose their deposit. Okay, so it works kind of like this. Somebody makes a disputable assertion, and when they do that, a timer is started in which everyone else has an opportunity to challenge it. If they don't, if time passes without a challenge, then it's confirmed that it's accepted as correct. Everyone had their chance to challenge it. They had an incentive to challenge it, and if they didn't, then they must have believed it was right. Alternatively, you can have an assertion, a disputable assertion made. Somebody can challenge that, and now you have a dispute between an asserter who made the claim and a challenger who says it's wrong. And we efficiently resolve the dispute through a two-stage protocol. The first stage involves bisection. That is the idea that once the challenge is made, the asserter has to bisect their assertion into two half-size assertions that fit together to yield the initial one. And then the challenger has to pick one or the other of these two sub-assertions to challenge. Here they challenge the second one, something's wrong with it. Maybe you didn't get to this end state. Maybe it didn't spend exactly these coins. Maybe you can't even execute n over 2 instructions. Whatever it is, he claims this is not a thing that this machine could do. So you continue this process recursively. dividing into 4. One of those gets challenged and so on. After a logarithmic number of stages of this, what you have then is an assertion about just one step of execution, like say an add instruction, and somebody has challenged that. Now at this point, we go to the second stage of dispute resolution, and this is the one that uses the virtual machine architecture, and that's a one-step proof. And so the party who has made the one-step assertion needs to provide enough information that an on-chain component can verify that their claim is correct or determine that it's wrong. And so the big question here is, how big is this one-step proof and how costly is it to create and verify? Through a bunch of trickiness in the way we design the virtual machine architecture, we make these one-step proofs of small constant size, meaning a few hundred bytes, and that's independent of the complexity of the contract, how much code or data it has in it. And they don't require complicated cryptography, just hashes and ordinary digital signatures. So the custom VM architecture guarantees that these proofs are small, and it's efficient. One-step proofs are this small, and they're fast to create or verify. It costs about 90,000 gas on Ethereum to verify this. So this is order of 10 cents or less worth of gas to verify a one-step proof. And they're also private. They don't leak contract data because they're just dealing with hashes of things. Okay, so one of the consequences of the way this design works is that the state of a virtual machine, of a running contract, is revealed only to its validators. They're the only ones who need to know. The only thing that appears on chain is this stuff: saltable hashes of the state, cryptographic hashes, the number and timing of steps executed when you're in non-unanimous mode, the fact that the VM executed some particular number of steps at some point in time, and also the messages and money that are sent and received by the VM. If the virtual machine is going to receive or make payments of ETH or of other tokens, that's ultimately going to need to be recorded on chain, and so that's going to be on chain. But this is all that appears on the Ethereum main chain. So Arbitrum runs on top of Ethereum. We have an Ethereum contract called the ETH bridge, we call the ETH bridge, which manages all of this, resolves disputes, and so on. Okay, so right, it's built on Ethereum. We offer a compiler that takes your existing Solidity code or takes EVM, Ethereum virtual machine code if you want, compiles it into our AVM architecture. So you can use existing contracts. We offer plugins on the front end for Web3, Ethers, and Go Ethereum to let you use your existing JavaScript or Go-based front end. You just plug in our plugin instead of whatever one you're using, so you can use your existing front end code. These virtual machines that are running can send or receive ETH or any ERC20 or 721 token between Ethereum land and Arbitrum land or to other Arbitrum virtual machines. This is all available on GitHub. It's open source. You can go and try it out. Okay, so we have a developer site, which is here, developer.offchainlabs.com. The code, as I said, is here in the URL. You can probably guess, github.com, Offchain Labs, Arbitrum. There's a developer quick start doc, and we have an API prize of $1,500 here at this event. And we have, I think, a few minutes for any questions.
As a scalability solution, can you give a high-level overview of how Arbitrum compares to other Layer 2 solutions, maybe such as Scale?
Sure. So where we are now in our alpha is we measure, for scalability, we measure a couple things. There's several things that are relevant. One is how many contracts can you run at the same time, and then what performance do you get for each contract. And performance for each contract we measure both in terms of transactions per second, that is sort of how fast can you spin the dial, and also how much computation you can do per second within a contract. Right, so in terms of the number of contracts per second that you can run simultaneously, when you're running on sort of testnet on a local machine, local laptop, so you can run thousands of contracts at the same time, and we can make that number, frankly. We feel safe saying thousands is an honest number, but we can cook the benchmark to make that as big as you want. In terms of transactions per second, we currently are a bit over 500 transactions per second in each contract. Again, thousands of contracts at the same time. the amount of computation you can do in each contract. Right now, each contract can execute instructions at a rate that's about 2.3 times the global capacity of Ethereum within each contract. That's where we are now. We expect to get substantial improvements over that continuing over time. So the other thing that we think is important for application developers is finality time, right? You want to be able to get instant finality in the common case, and you want to be able to do that with a very strong trust guarantee. There are lots of different level 2s out there, and there's different trade-offs between them. We think we really hit a sweet spot in terms of scalability and performance, privacy, instant finality in the common case, and a very strong security guarantee, right? So unlike some other chains which say you need to have half honest or 2/3 honest participants in order to guarantee a correct execution, we have this very strong antitrust guarantee. So even one honest validator gives you a guarantee of correctness. So it's trustless with respect to those participants. So that's basically what the trade-off is there.
Good, thank you.
Sure. Anybody else? All right, yes?
Do you imagine that because of the particular nature of the proofs you have, that this is better suited to like certain types of applications than others? Like you could imagine because the proof you have is like computation based, there might be certain things that this might not work for.
So, I mean, it does work for everything in the sense that you can compile any Solidity program, and the compiler doesn't generate a slowdown compared to other dispute resolution-based systems. So, in other words, it is general purpose in the sense that you can run anything on it.
Okay.
It's especially well suited for applications that require a lot of storage or a lot of computation, because the on-chain footprint and the cost of proofs and so on are independent of the amount of storage. The cost of dispute resolution depends only in a logarithmic way on the amount of computation you do. And so things that require large storage or lots of computation, and in multi-user type dApps, large storage may come from having a lot of users whose records all need to be kept within the app. We also have a particular type of privacy guarantee, and so if you care about that, we also might be well suited for what you have. We kind of feel like we have a combination of features that is really unique as well. So if all you care about is privacy, then maybe you want something. If all you care about is scalability and you're willing to sacrifice some security in order to get it, then maybe something else is right. But we think we're at the sweet spot where we do well on all of these dimensions.
So is this fully open source?
Yes. Yeah, the current version is open source. There will eventually be a premium model, which is a premium version, which is closed source. But the developer version we have out now is BSD licensed and will always be open source. There will always be a fully working system at least the current performance characteristics that's open source.
What features are you planning to add to the premium version?
It'll be higher performance, and primarily higher performance and some tools for sort of management and accounting. The sort of things that we think enterprises are likely to want, in addition to higher performance.
So can you say more about this only one honest party
Yes.
needed?
Yeah.
So basically you're saying that you divide the code, you can do like a binary search in the code for
Yes.
the thing that people are contesting,
So yeah, let's go back.
and then you need to and then someone has to prove
Yeah, so
that
So let's walk through the example a little bit more carefully just to kind of put a finger on that, right? So suppose that I make a claim like this, right? And you actually you know the initial state of the VM, you run it for n steps,
Yeah.
and you find that it ends with some other hash,
Yeah.
right? So you would then just put down a challenge on my claim, right? So now it's you versus me. And this Ethereum contract, the ETH bridge, is refereeing our dispute. right? So now it's my turn. I have to bisect my assertion. Now, it's pretty easy to prove that if my initial assertion was wrong, then at least one of these two halves has to be wrong, right? And so your job, once I have made this claimed bisection, is to figure out which half is wrong. What you're going to do in practice is you're going to try to replicate the first half. If that's wrong, you'll challenge it. If it's right, then the second half must be wrong, and you just challenge that.
So we have like an instruction number, and at that point we stop,
Yeah.
check the hash.
Check the hash. It doesn't match. That's what you do.
Yeah.
That's what you did to figure out if I was right in the first place, right? And now when I bisect, essentially what I'm doing is I'm saying, what was the hash at the halfway point? I'm making a claim about that. And you say either that you can't get from here to here in n over 2 steps, or you can't get from here to here in n over 2 steps, right? If my initial claim was wrong, at least one of these two sides of mine has to be a lie. You just have to figure out which one it is. You put your challenge on that one, right? So now you've got your finger on something that you know is wrong that's smaller, right? You don't know what I claim happened in here, but you know this is wrong, right? So this happens on chain, right? I've made this assertion on chain, and you put the challenge on chain, and I wrote this midpoint hash on chain, and then you said, well, I'm challenging the second half, and so on. And we continue to do this,
So
right?
now I put down 2 deposits?
No.
No.
I put down a deposit when I made my first claim, and then you put down a deposit when you made your challenge. And now we're involved in this dispute, and we're playing for our deposits. The loser's going to lose their deposit, the winner gets half, the other half gets burned. Right? And so if your challenge is a valid challenge, at each stage you'll be able to identify one of the halves that's wrong. And so you're basically pinning me down step by step, assuming I'm lying. If I'm telling the truth, then I just keep telling the truth. And so we get down to the end, and if you were right in the beginning, then you're going to be right down here as well. I will not be able to show that you can get from here to here in one step of execution. If I was right in the beginning and I told the truth all the way down, then your challenge was bogus and continued to be bogus all the way down. So whoever was right at the top level is also right down at this level, assuming that the person who was right played the game well. And so then the on-chain component just needs to resolve this dispute, right? And that is the point where I have to actually, what my claim has here is a hash of the state. I have to open up a little bit of that hash. You can imagine the whole state is organized as a Merkle tree, and I have to open up a little bit of that Merkle tree, just enough that you can figure out what the Merkle tree after one step of execution is. Just enough that you can figure out, oh, it was an add instruction and he was adding 3 and 7, therefore the result is 10, and the rest of the big Merkle tree is just what it was before, so we don't need to open it. Right, and so that's kind of the spirit of how that one-step proof works. And that's checked by an on-chain contract, costs about 90,000 gas to do that. And now it knows whether I was right or you were right, and whoever was wrong is going to lose their deposit. Right, and so what that means is if whoever is right will win. And so if I was right in asserting that what I was doing, I will win the dispute. And so because this dispute gets to the truth of what a virtual machine would have done, with some technical caveats that we could talk about off-chain. In other words, which don't lead to incorrectness of the outcome. Right? Maybe both people are idiots. The point being, maybe both people are idiots. And the protocol is designed so if both people are idiots or lying, that it doesn't take a wrong step. So what we guarantee is that any one honest party can prevent a wrong action by challenging it. And then, although I didn't talk about it in the limited time I had here, we also guarantee antitrust progress, which means any one honest party can force progress even if everyone else is throwing up fake challenges at large expense to themselves. And that's how we get the antitrust, basically, that whoever is right is able to win because they're right. That's the thing you have to do in order for one right person to be able to win over n-1 wrong people. You have to actually get to the truth of the claim.
So I guess progress in the evolution of the contract needs to be frozen during this dispute process because you don't know what the correct state is.
Not quite. So one thing you can do is you can take those two parties and send them off to the side to resolve their dispute. So once the dispute starts, so if the original asserter wins and the assertion is accepted, the system can't necessarily believe that that assertion was correct, right? Because maybe those two parties were actually colluding and trying to create a situation where the asserter won. And so if there's a dispute, you just take those two parties, you send them off on the side to resolve their dispute, and then the operation of the virtual machine can keep going.
So what's sort of the worst case delay in the dispute resolution process?
So the worst case delay is assuming that there are n-1 people who are willing to lose deposits, willing to lose large deposits repeatedly, they can slow you down by basically a factor of n. That's right. But if you make the deposit...
If you do this push off to the side, how long is the dispute resolution?
The dispute resolution, let's see, so it partly depends on n, right? So it's log of n. We don't really bisect, we really do k-way k-section for a larger k. So under realistic circumstances, think about a dozen on-chain transactions to do the dispute resolution. So you can send them off on the side to do that. There is a large, they have put down large deposits, and those large deposits, the loser's deposit, half of it will be burned. A little bit of that actually goes to compensate the miners to pay for the gas to do all of the dispute resolution. So there's ample funds from the loser's deposit to basically pay for this.